Hi everyone. My name's Kevin, and the theme of my session tonight is based on statistics and simulations. In particular, a selective subfield known as Bayesian Statistics that is a bit more rare in the classical statistics that we probably find very dry in our university days. But in the interest of time, I will be simplifying our slides quite significantly, and if anyone is interested in the more technical details, I'm more than happy to discuss it after the presentations. With that, let us get started. Okay, so for the agenda for this session, I'll briefly start with an introduction on Bayesian statistics. Then I'll go into how you can achieve this through Solvexia, and I thought one thing that we'll do after showing you how to do these things in Solvexia is show you an algorithm that was designed to be easy and accessible to all ranges of audience so that they can make use of the theory without needing to be enticed by the technical details. And I'll follow that up with a toy example to demonstrate why this algorithm just works and is sufficient for most of our everyday lives. And then I'll end and conclude with why we use it and how is it used in today's society. So let us start by taking a step back and thinking about how do we as people learn and how do we evolve over time? The basis of how humans think is we generally have a belief of how things work in this world. But then as we experience our everyday lives, those beliefs change and they update. And that's how we develop as humans. And that is the core of what Bayesian statistics is trying to achieve, is to emulate that human learning method. So if I give you an example, when we usually lose our house keys, there's usually one location that we always jump to first. But if you don't find it there, you go to the next location. However, if you lose your house keys 10 times in 10 weeks, and your first location you don't find your keys in the first location, you begin to shift your mindset. So let's say, hypothetically, I find out of nine out of 10 times, my house keys are in the freezer for some reason. On the 11th time, I won't be looking in, say, my bedroom. I will go to the freezer to pick up my keys. Don't know why they're there, but they are. So that's the basis of what Bayesian statistics is. And if we think about it, how did this come to be? How did people develop this imitation of human intelligence? So we can trace back the original theory and the concepts back to the 18th century where Thomas Bayes first proposed the idea and then was lost until Laplace picked it up and constructed the framework that we use today. And that's the equation, fancy equation that we see on the slides. And then unfortunately after Laplace, the method fell under the radar until more famously in World War II where Alan Turing used the Bayesian statistics to crack the Enigma code. Fancy. So, yeah. So what is this Bayesian statistics that I've been going on about? So I thought the best way to describe it is through an example. So personally, I want to budget my spending. I have a pretty good understanding of how my monthly spending patterns are. So I'm capable of expressing that belief of how I spend. And that's represented by the blue line. And formally that's known as your prior belief. And then I go digging through my bank transaction account, and then that data tells me something different, and I construct some sort of formula to represent the component that we call, what does my data tell me about how I spend. Yeah? So the Bayes theorem basically says, if I combine these two, I get that green line, which is what we call an updated belief. So it's the imitation of the process where we observe something and then develop as people. So how do we do these sort of fancy stuff in Solvexia? There are two good tools that we use. The first one is R, and the second one is using the managed table, and we find them both very good. It then works out very well. So I'd like to jump ahead and go through the concept of this algorithm that academics have developed. So one problem with Bayesian statistics is that you need to construct a complicated and usually very complex mathematical formula. So one thing that academics have developed is something called approximate Bayesian computations, which allow you to bypass the construction. As long as you have a model to generate data, which most people use, you can use it. So the algorithm basically says, sample your intuition. Using those intuition, generate a data set from your model. Does that generated data set reconcile with your observed data set? If it's close enough, you retain those parameters. And once you've retained enough of those model parameters, you get something known as the posterior, which is your updated belief. And then you can use that sample to make your predictions. So going back to my spending example, one thing I want to do is, maybe I'm just too lazy to construct that orange line over there, but I want to use, and so I can use the algorithm to generate the green line. So for demonstrations purposes, if I start off with a very loose definition of what I mean by close enough, I get a pretty bad line or imitation of what the theoretical truth is. But if I strengthen my definition of what is close enough, you get something better, and if I strengthen it a bit more and a bit more, I eventually get back what the truth is, or at least theoretically. So just to keep going on, why use it? So there are a few reasons why to use it is to express your uncertainty in some of the models you've developed or analytics. So often not, we are always asked to say what is the most probable value, but no one takes into account maybe our most probable value only has 20% to occur. So we would like to see, or at least I would like to see, what constitutes the other 80%. And that's one way we can use Bayesians to do it. Alternatively, sometimes you're just curious about how you would develop your own intuition based on how data. And it gives you a quantitative way to develop that. Whether it's useful, it's always a personal belief. Skipping the model's choices, because it's pretty common, if we do, another thing is tiny data sets. So while big data is very popular and the most, what everyone is interested in at the moment, one thing that computers, no matter how powerful computers are with, it will never help you deal with a lack of data. So tiny data sets, as some people have termed it. So how can I predict or make analytical judgments based on, let's say, a new product and you only have 1 year of data? So the Bayesians allow you to incorporate the expert's knowledge and intuition to construct a much more meaningful analysis. So how is it currently used in society today? It's actually quite popular in population genetics, where people basically use it to predict how genes vary across populations. It's actually quite popular in some insurance pricing via credibility theory. We actually use it through worker compensation schemes. Yeah, and it was first proposed by an actuary known as Arthur Bailey. Another aspect that some engineering companies use is for risk analysis. Manufacturers might be interested in when the equipment failure will occur, given that it's been handed out for, let's say, 6 years. Lastly, it's more popular is social networks. I'm sure if anyone's used Gmail, you've been getting suggestive ways to complete your email. That's how they do it in some sense. Alternatively, some people use it to classify how some emails are considered spam. And that gets updated as people move on. So that's the crux of my session. So thank you for listening. Hopefully that was interesting. If anyone has questions. All right. If not, I'll pass to Ivy, who will now talk about smart contracts.